So apparently we may or may not be moving to online-only mode after spring break. I'm still waiting for more official news before we say more concrete things. Yes.
On the UB coronavirus website, it says that on the 23rd we're officially moving.
On the 23rd? Okay.
March 23rd,
So-
which is the end of spring break.
Okay. So we'll see where that goes. I'll still wait for some more official university level thing, but it does look like that's what's going to happen. So far, all I've seen was a tweet from our governor, which is ridiculous. But so the website, they might have seen that tweet and updated, is what I'm guessing. Where actually, let me take a look at that. Where'd you on the coronavirus part of the UB site? We have a coronavirus dashboard. Oh my. Yeah, all they heard was the governor's announcement too. Looks like. And then UB is going to make a more official announcement. I'm going to wait for that official announcement. We probably know what it's going to say, but we'll see. I'm going to hedge my bets just a little bit before everybody's just talking about the tweet. I got there's chatter with Chun Ming. He sent in us emails saying that he read a tweet too. Looks like that's what they did too. This world we live in drives me nuts sometimes. Can we just get an actual official word? Is Twitter the official word? A tweet from a politician and we all change our lives and panic. Everybody's worried about meal plans and stuff. Can we just get an official, this is the word? Is that so much to ask before politicians create mass hysteria like this? But anyway, so what this means for this class, with labs is the big question. I got to figure out something with that. So if we are going to online-only mode, especially if it's lasting the entire semester, that's the part that really drives me nuts. That seems just tongue-in-cheek, like, for the rest of the semester, I guess. Like, it doesn't seem like an official thing. I would guess there would be a sooner end date than that. And does the end of the semester mean the end of classes and we come back for just finals week? Like, that's the kind of stuff that I really need to know. For labs, though, a lot of that's going to hinge on what official word actually comes out. For labs, I don't know, I'll just think about it over spring break and come up with some brilliant idea and we'll be able to get through it and everything will be great. For lecture, we're already in online mode. I'm gonna stream on Twitch still, just business as usual, except I'll probably just stream from home instead of coming into work. But even if I do come in, I'll get great parking, so I might come in and stream from my office, who knows. But it's business as usual for that. I'll be streaming on Twitch. My office hours, I'll do those on Twitch. Some of the TAs have already been doing Twitch office hours, and more of them they're all talking about setting up their Twitch channels and getting their Twitch office hours. So I'll just update the course website with all the links to everyone's channels, or if they share channels, whatever the logistical details are, we'll figure that one out. And you'll be provided with all the links. Of course, we'll keep leveraging Piazza. You can keep chatting on Discord. All that stuff's business as usual. You just don't have the live meetings like this and the live office hours. All that will be Twitch only. Is there a comment? Did I answer that and all that rambling?
I just want to know, would you know if buildings would be closed?
I have no idea. We got a tweet. So at noon, the university sent out something that said, we haven't made a decision yet. And then at 2, Cuomo sent out a tweet. I know as much as you do at this point. There's no real information. It's just hysteria based on Twitter. It's crazy the way things work these days. But once we get some more official word, what I'm saying is I have no information more than you do, or more than just some random person halfway across the world has, for that matter. We don't have any access to more information. It's weird. And then the news articles, from what I can tell, the news articles are just reporters who also read the tweet, just saying, Cuomo said this. This is how we do things? Anyway, any other questions about this or anything else about the course or life in general? Anybody just want to chat about something?
How you doing today?
I'm doing all right. I had to wait for my food for so long. I didn't have time to eat it before lecture, so I'm going to be eating during the meeting.
I guess take over, you can eat.
Yeah, you want to teach so I could eat some food? I scarfed down like half of it as fast as I could before the previous lecture. But I'm also wondering, since we're talking about it, why do they have bags that are significantly smaller than the containers of the food that they give? It seems like a pretty obvious oversight. I'm sitting there fumbling with the bag. Or anything else? I did not have time to eat breakfast. That's why I grabbed this. I was hoping to actually get something to eat. And I only got a few bites of it.
Bring Jesse food for extra bites.
It's not even that. It's I don't have time to eat. That's where I'm at right now. Oh, it's tough. Anyway, I need more time in the day. All right, let's get into this. Immutability. So we've talked about immutability quite a bit throughout the course, but I mostly just kind of mention it and say these things can't change. You have to re-sign references and things like that. Today and Friday, we want to shine a bigger spotlight on this and say, okay, what's actually happening with this immutability stuff? To the end of having objects that can't change state, the lecture question today is to write an immutable point class. It's going to have one constructor that takes two doubles named x and y and use val for these. These are going to be values that are accessible from outside of the class, and they have names. So in your testing, you can say if you have a point stored in a variable named p1, you can do assert p1.x, assert equals doubles p1.x, and then whatever you expect that to be. So we can access these for testing, is the big reason why that's set up specifically like that. Val, doubles, named x and y. This point, the x and y values of this point cannot change once the point's created. So, but there are things that we want to do to modify this point. We want to be able to add another point to it, and I'm thinking vector addition when I write this. In hindsight, I probably should have called this vector. But I want to add 2 points and multiply a point by a scalar. So to add a point, I want to be able to take the point that this is being called on and the point from the parameter point and component-wise add each value. So I want to add the x's, I want to add the y's, but I have some change that I want to make to this point, but the point is immutable. And this is where the conversation of immutability, this is where most of the conversation happens. How do we do this? How do we simulate this change in a point when the state can't change? Well, we're going to create a brand new point. We'll create a new point with that change reflected and return a reference to that new point that we created. Same thing with multiply by scalar. This is going to take a double, and we're going to multiply that double by each of the components, x and y. So we're going to multiply those and return a new point with that change reflected. So we're not changing a point ever. Once it's constructed, once we have this object, its state cannot change ever. But if we want to simulate some change, we're going to create new points and return references to those points to be able to get the functionality that we want. So test this thing. When you're testing, there's one thing to watch out for with this one. I named this thing point. Now, point, there are a lot of classes. I think my autocomplete showed like 6 or so other classes named point in the standard libraries between Scala and Java. Make sure when you're testing, you're importing functions.point. This is something that at this point in the semester, I want to start throwing these kinds of things in there, so make sure that we understand packages and imports. If you're wondering, earlier in the semester, if you did physics engine, I have this class named physics vector. We've seen it in lecture a lot too. Physics vector, if you're ever wondering why I named that physics vector, it's because there is a vector class in the standard libraries. And if I name it vector, there's going to be a lot of headaches. There's going to be a lot of questions in office hours and on Piazza. where students are importing the wrong vector and they're not seeing any of the changes that they make in their code. They're not being reflected and just everything's generally broken if you import the wrong vector. That's something that can happen here. I'm opening you up to that possibility to make sure, so I want to make sure I mention that and let you know to be aware of that. Early in the semester, in those first 3 weeks are pretty chaotic as it is. You're figuring out what Scala is, you're figuring out what IntelliJ is. I don't need to throw something extra in there. So I named my vector something silly like physics vector, because I know nobody else is going to use such a ridiculous name. Why would you call it physics vector? It's ridiculous. But if I name it that, I know nobody else will name it. There's not going to be another package with a physics vector class. So we're not going to have that naming conflict issue. And I'm preventing just one more thing that I would add on to that stressful first 3 weeks. At this point, things are cleared up a bit. You're comfortable with Scala. I'm going to name this thing point. So watch out for that. Make sure you're importing the right point, which is, I mean, that's going to be something throughout your career, making sure that you have the right class. We have classes. We can have classes of the same name as long as they're in different packages. It's just something we have to watch out for. Are you importing the correct thing? This will come up again when we talk about GUIs. This is going to be critically important. We're going to use Scala FX, which is an adapter library for Java FX. So we have Java FX and Scala FX in the same project. And both of these libraries have a lot of the same class names. And sometimes we want the Java FX version, sometimes we want the Scala FX version. And getting that right class for our specific application is pretty important. It breaks the code if we don't have the right one. But in a really confusing way. The errors don't help us much in that case. It's just going to say, I was expecting an action listener and you gave me an action listener. Well, that doesn't help me. So we want to start getting used to that idea. So I'm sneaking it in there in this lecture question. That is intentional, is what I'm saying. Make sure you import the right one. So immutable objects. Objects where the state cannot change. We have some initial state. Usually we're setting through a constructor. I guess always we're setting through the constructor. If we have an immutable state that's not set through the constructor, it's just a strict constant. But anyway, we cannot change state once we create the object. The state of that object has to always stay the same. It cannot change in any way. So if we want some change made to this object, how do we do that? We're going to return a copy of this object with that change applied. And it's going to be the big theme throughout this lecture. I'll probably say this more times than you feel like you're listening to. But we're going to return a copy of the object with that change applied. So let's see an example of doing this. I have this kind of silly class, kind of an academic style class. It's just used for an example in a lecture. You would never do this. But I have some counter, some immutable counter, which is going to initialize to some integer. And I have two methods that can either increase the counter by 1 or decrease the counter by 1. And this is the only thing I can do to the counter. But it doesn't actually change the counter variable because this is immutable. That's our whole idea. I didn't use var here. I didn't even use val. So this counter is actually, this int is not even accessible from outside of the class itself. The only thing I can do is print it to the screen. This is really the artificial part. Why would you ever have a method like this? You just put val here and access the counter and then print it. But I have this one method just so we can see the value of counter, but we don't have any access to that variable directly. So I'm kind of artificially restricting this just so I can sneak in a recursion example. I can force a recursion here. So we can't change counter, but what we can do is return new counters with that change reflected. So if I want to increase the count by 1, I'm going to read the counter, add 1, and put that in the constructor of a brand new immutable counter, return a reference to that, and return that new counter. And to the recursion note, recursion, even though we're not talking about recursion directly, it's not a recursion lecture, I am going to constantly get recursion examples whenever I can sneak them in there. I think recursion is one of those things where You just got to see, if it doesn't make sense yet, you just got to see example after example after example. So even when I'm talking about immutability, I want to keep reinforcing recursion because it's a tricky concept. It takes a while to wrap your head around what's really happening with recursion. So I'm going to sneak a few examples of it. We're going to see 3 examples of it in today's lecture. So this, so say I want to increment the counter 10 times. So incrementing once or twice, we call one of these increase or decrease. We can create a new value and assign that value the return of increase or decrease. So one increase, one decrease, it's no big deal. What if we want 10 increases? Now this is where we would usually, before recursion, this is where we would throw in a loop and use a var. We would take a variable, we would say like var counter equals new immutable counter of 10. We would have a loop that says for I, something like, this is how I would approach it anyway, for I in 0 until 10, which is going to loop 10 times. And the body of that loop is going to say counter equals counter dot increase. So I'm going to call increase. That's going to create a brand new immutable counter on the heap. I'm going to return a reference to that new counter, and I'm going to reassign it to the variable that was storing the old reference to the original counter. And then as the loop goes, I'm going to keep creating new counters and reassigning it to that variable. And then by the end, I'm going to have that a reference to a counter that has been increased 10 times since the original counter. So that's how we would normally do it with iteration. We've written loops before like that. It's basically the accumulator pattern, but with a little bit different setup with the immutable objects. So that's how we would normally do it. But again, I'm artificially restricting this one so we can see how to do this recursively so we get more practice with recursion. So we're ready for those examples where recursion is going to be the best, the easiest, simplest option. I don't want you to panic when we get to those and not know what recursion is. So we're going to get some more recursion examples in here. And specifically when we get to trees, working with trees and doing tree traversals without recursion is painful, to say the least. It's really tough to navigate a tree without recursion. With recursion, it's basically trivial. But let's talk about this. So my base case here, I have some trivial input-output behavior. Oh, and I didn't mention this last class, and then it caused some confusion. What I'm trying to do here, update counter, I want to give it a counter and say either increment or decrement this many times. So I say update counter 20 of counter. I want this to return a new immutable counter that's been incremented 20 times. So this counter 2, that print count, this should print 30 to the screen. If I gave this negative 30, if I said negative 30 counter, I'm saying I want to decrement this 30 times. I want to decrease the count by 30. That would return counter 2. Print count in that case would be negative 20. If I started at 10 and I say subtract 20 from this 10, then I would be able to get that. So that's my goal for update counter. That's what I'm trying to do. The trivial case is n equals 0. If you say, give me this counter, but change the internal count by 0, well, I'm already done. You asked me to do nothing. Why'd you even call this method? So I'm just going to return the counter. Whatever counter I get, if n is 0, just return that counter. Trivial input-output behavior. I don't have to do much thinking there. If you tell me to change the counter by 0, that's no change. Like, why? And of course, there's a reason for that, because it's our base case. If it's not our base case, we're going to hit one of our recursive cases. Whether if n is negative, that means we want to decrease the counter. So I'm going to make my recursive call. I'm going to decrease the counter. That's going to give me a new immutable counter with the counter decremented by 1. Then I'm going to increase n by 1 and make the recursive call. And I'm going to write this logic assuming that the recursive call is going to be correct. So if update counter of this new counter that's been decremented once, if this recursive call is correct, I'm going to give it this counter decremented once with n plus 1. That should give me the original counter decremented n times. If n is negative, for example, if n is 3, and I decrease this by 1, that's the same as saying give me this counter decreased twice, -2 times, as opposed to -3 times. Same thing on the positive side. I want to decrement n by 1 and increase my counter by 1. So reflect one of those increases, and then make the recursive call saying I need n minus 1 increases now. That's how many increases are left to be called. So I have my base case, trivial input-output behavior. I have my recursive calls. All my logic, just assuming that my recursive calls are going to be correct. And my recursive calls are always getting closer to the base case. I have my 3 ingredients for some successful recursion. This thing should be working well for me. Any questions on this example? All right. So that was an immutable object. Let's talk about, let's bring back this stack and heap and talk about 2 of the immutable types that we've seen throughout the semester, strings and lists. We'll see an example of each. Strings, I've mentioned throughout the course, these are immutable, and I make a big fuss over it, but I've never talked about what that means. Now is the time to talk about what that means. Before, I just said strings are objects. They don't map to a primitive type. They don't go on the stack. They go on the heap. They're objects. But we're going to pretend that they go on the stack. And I basically left it at that. I said they behave like they're on the stack, even though they're on the heap. They're on the heap, but we don't get this reference behavior. We can't give a method a string and see a change to that string. We can't get some change on the heap on that object like that from a method accessing it by reference, because the string is immutable. The characters of a string cannot change. Once you create a string, those are the characters for that string forever. They cannot change at all. So that we get that behavior as though it were on the stack, but it's not. It's on the heap. So let's demystify that and see what's going on with the stack and heap with strings. And you can count on whatever form and shape the next lab ends up taking for the functional programming learning objective verification lab, whatever shape that ends up taking. You can count on stack and heap diagrams. This is one of the ways that you can make up that first learning objective, the third bullet point of the first learning objective, that stack and heap stuff. This is where stack and heap is going to make a triumphant return, and we're going to look at the, I guess it returned on Friday as well, last Friday, looking at recursion on the stack and immutable objects on the heap. Those are going to be the 2 ways that you can prove that you have that stack and heap knowledge to finish up objective 1 if you're in that boat, that you need to, that you got that feedback. You can complete this on future activities for learning objective 1. This stuff is going to give you an opportunity to show that. So let's take a look at this program. It's going to create some strings. They're objects on the heap. We're going to look at how the heap changes. We're going to look at how the stack changes. And we're in the middle of the execution right now, skipping some of the steps that we know from the last time we looked at stack and heap. But I want to just quickly recap what the program has done up until this point. So we started with main. We created this string, which looks like a string literal. This is what we would call a string literal, and I'll probably call it a string literal in this lecture throughout this example. But what this is actually doing is calling the strings constructor and saying, give me a new string, a new object of type string, allocate space for it on the heap, allocate enough space to fit these characters, allocate enough space to fit these characters, and then give me a reference to that string. That's what this is what we would call a string literal, which I guess we can just call it a string literal, but it is creating a new string object. So this is going to create a new string object, put that on the heap, allocate memory for it, and return a reference. Wherever that is on the heap, it's going to give me a reference to that object on the heap. So this, in this example, is going to resolve to @1. And I'm going to assign that to this new value course of type string reference. Course is going to store that value @1 and refer to this string on the heap. Now strings are immutable. That object on the heap can never change. This @1 is always going to be CSE 116. Always, 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 it cannot change. Because it's immutable. Because strings are immutable. in Scala, but also in a lot of languages. Your strings are immutable in a lot of languages. Then we get to this, this call of nerf. We're going to put that frame on the stack. We're going to resolve the argument and assign it to the parameter. Input has that reference of 1, so we just pass this string by reference. But of course, we're not going to get that reference behavior. We're going to call input, so at1.replace 6 with 5. We're going to go to this spot on the heap. We're going to follow the reference of input. And we're going to call replace on this and replace all the 6s with 5s. We can't change that string, so as immutable objects do, we're going to create a brand new string, allocate memory for that on the heap, and return a reference to that object on the heap. So input.replace 5, 6, that's going to create this string and return this reference at 2. So this returns the reference at 2, which is a new string with that replace applied to it. And this is where, in 1.15, we all get tripped up, where you call some string.replace, and you would expect the reference of input. You would expect this string to be changed after that call of replace. And you pull your hair out, you go nuts, you post on Piazza, you go into office hours, and eventually somebody's TA or instructor or your friend or somebody says, no, you have to say input equals input.replace. And you go, why do I have to do that? It's a thing that we all go through as we learn programming. Because that change is not made to that string, because strings are immutable, you have to reassign it to the variable if you want to see that change, if you want that change to reflect in that string. Yes?
Why in Python, when you do replace, it only replaces first character, not all of the characters
In Python, oh, you're going to test my memory on this one. In Python, is it Python you have to call replace all, and then it replaces every instance? And then I know in JavaScript, the replace only does the first instance until you do the /g to replace it globally.
Why is that?
It's just how they design the languages. I don't know. It's just how they built the standard libraries. I don't have a good answer for you on the why, but yeah, certain languages are built differently. For why JavaScript does that, I can give you a little bit better answer. It's because JavaScript is kind of a crappy language. I'm realizing I'm on stream when I say that. That's eternalized forever. But JavaScript was built very quickly. It wasn't really intended to be a major language that so many people use. It was such a fundamental part of software engineering. It was thrown together quite quickly. There were a lot of design decisions that were just made off the cuff. So we end up with this language that started out with a really crappy foundation, and then it kind of evolved over time, and with each update, it kind of got hobbled together to fix it. But it's just a fundamentally poorly designed language. But unfortunately, we're stuck with it, because that's the language that won the internet war. Like, that's the language that we use in the browser, so we're really stuck with it. And unfortunately, it's crept onto the server side too with Node, but it's a separate story. And it's, I don't know, once you get used to its quirks, it's not too bad, but yeah, JavaScript is really weird. But what's that? Yes, absolutely. But Python, I think Python you can call replace all and it will replace every instance. I think you can get around it with that. But JavaScript certainly, JavaScript is just painful. A lot of things like that. Like, why do I have to do the /g? Why don't you just do the behavior that most other languages do? Or at least give us a replace all method. Yeah, I share your pain on that one. But yeah, we all have to suffer through JavaScript. It's just part of our lives now, unfortunately. So one side note, I forgot to put these in the slides, but even if I remembered, I probably wouldn't have done it anyway. I would just have it as a side note like I'm doing here, just because it would clutter up the slide a lot. But when I have these string literals here, this 6 and this 5, this would also create 2 more string objects on the heap with those values 6 and 5. So I would have another object here with just 6, another object here with its own reference of just 5, and then those references are passed as arguments to the method, and then the method takes those 2 references and the calling reference that's in this, and then does its magic with those 3 references to create the new string with those values replaced. So there would be a lot more strings on the stack. The 116, the 250, the is great, the is fun, all of those would also end up being separate strings on the heap. Did I say stack? I meant heap if I said stack. Those would all be separate objects on the heap and passed by reference into these methods that they're being called with. So there would be a lot more going on over here for each one of these literals. So replace, all right, picking up where we were, this replace is going to create this new string. It's going to return this reference at 2. So this expression resolves to that reference at 2. And then this method, it returns unit, so it's actually not going to do anything with that reference. It doesn't return it. Even if we were returning it, we're not assigning it to a variable or a value. So when we move on with our code, we don't even have any reference to that string CSE 115, that string with that value. This string at 2, we didn't do anything with that reference. We just left it on the ground. We couldn't even return anything anyway, and then we wouldn't assign it to anything anyway. So for a lot of reasons, we no longer have access to that string. That reference at 2 is completely gone to us. So after that method call, we actually have no change to the state of our program. Nothing at all changed. The stack is in the complete same state as it was before that method call. The only difference is that we have this reference on the heap, this object on the heap that we don't even have a reference to. We have no way of accessing this object on the heap. And this is a case where this would actually end up being garbage, could end up being garbage collected, depending on how the JVM feels like optimizing at that moment. But this object, since we have no reference to it, we can't do anything with it. And then when the JVM sees that, when it sees an object on the stack, on the heap that we don't have a reference to and no way of accessing, it can delete that at any time with something it calls garbage collection, where it's going to remove this object, free up that memory, and give that memory back to some other process or whoever else needs that memory. It's going to avoid what we call memory leaks, where we're creating these objects that we're not using anymore. It's going to clean all that up for us and manage our memory in ways that it's optimized to do. This is something that exists in Scala, exists in Java. It's part of the JVM which Scala is running on. It exists in Python, it exists in JavaScript. So you haven't known a time without garbage collection of how much this is doing for you. But in CSE 220, you're not going to have garbage collection anymore when you start coding in C. And that's a big part of that course, but a big part of the reason why it's taught in C is because the course is teaching you how to manage your own memory. And going into the heap, you're actually going to write the commands to ask for memory allocation, get memory on the heap, and then write your data to that heap memory that you requested. So in 220, you're going to talk all about this. Okay, you've had garbage collection, you've enjoyed garbage collection for 2 semesters. What if you didn't have garbage collection? What do we do now? And that's where you're really going to dive into this understanding of stack and heap. I'm laying some foundation work on stack and heap in 116. 220 is going to take it to a whole new level. So you'll gain a lot more understanding of what's going on here in 220 when you really get your hands on this stack and heap memory. Right now, I'm mostly concerned with can you follow the references and know what's on the stack and what's on the heap. 220 is going to really ask you to manually work with the heap. So that's where you'll get to learn a lot about that stuff. I feel like I talk about 220 or 250 quite a bit in this class. I talk about how that's going to show you how to optimize things. But I want to give a shout out to 220 as well. 220 is going to dive in. One of the topics of 220 is going to dive into that memory management. How do you manage your own memory when you don't have a garbage collector anymore? And how do you optimize that part of your course, part of your code? Okay, so nerf didn't do anything. Let's see if amplify can do something for us. So amplify, we're going to pass a reference the reference course, which is pointing to @1, which is this CC116 string. That's going to get that input of that reference, call replace 116 with 250. Replace is going to do the same thing it did last time. It's going to create a brand new string with the change reflected and return a reference to that string. So this resolves to the reference @3 in this example. We do have our return type, so we are returning a string reference. That string reference is being stored in a value this time. So we're creating a value and storing that reference in this value. So when this method call returns that reference of that new string that was created from the replace method, we're actually going to assign that to a variable, and now we do have access to this string outside of that method call. We didn't just leave it on the ground and walk away from it. We actually returned a reference, stored that reference, and now we have a reference on the stack to that object that was created in the method call. So now we actually can work with this string. We can work with this CC250 string. Next, without calling any intermediate methods, we're going to call the concatenation method on course. Course, still storing that reference to 1. Course is a val, so for its entire life cycle, it's going to store that same reference. That reference is immutable, so it's always going to store the same value. So I can always count on course referring to the string CC116. That's one of the advantages of immutability. So course, we're going to call the concatenation method on this new string. Again, this would be another new string on the heap. Concatenate is great. That's going to create a brand new string. CC116 is great. Return this reference to that new string @4 in this case. So this whole expression, which is a method called to the concatenation method, this is going to resolve to @4. But just like that first method call, we leave it on the ground, we walk away from it, and we don't do anything with it. We didn't reassign it to anything. We didn't create a new value and store it in a value. We didn't use it as an argument for a method call. We didn't do anything with it. So that line has no effect on our program at all. It created some memory. It used up some memory on the heap, but it didn't have any effect on the functionality of our program. We just walked away from it and left it there. This, again, one of those common mistakes in 115. We can talk about it in lecture, but we always hear it in office hours after. If you want this change reflected, course would have to be a variable, and you say course equals course plus is great, and then the course variable would no longer refer to @1, but it would refer to @5 instead, or @4 instead. We would reassign that reference, update the reference to be able to point to a new object on the heap instead of pointing to the immutable object that it's been pointing to, which is never going to change, which cannot change. You would update the reference that it's referring to a new reference, and then you could see that change. And of course, we're not using var, so we'll create new values each time we want to do that. Like in this line here, course string of type string is going to equal course CC116. Concatenated with is fun. Again, is fun would be another string on the heap. That creates this brand new string, returns a reference to it. We assign that to this variable, and we have course string pointing to @5, which is going to be this reference here. And then when we get to our print statements, we're going to print course @1, CC116, data structures @3, CC250, course string @5, CC116 is fun. 2 and 4, these two strings, we don't have any access to. By the time we get to our print statements, they might have been garbage collected. They might be there, they might not. We don't know, we don't care. They have no effect on our program at all because we don't have references to them. Any quick questions on this one? All right, let's do lists in 10 minutes. Lists are immutable. You've heard me say this a billion times also. Let's talk about what this means and how this affects us in terms of stack and heap. So let's look at another example. I'm sneaking in 2 more examples of recursion here so we can talk about recursion a little bit throughout this example. Let me quickly talk about what this code is doing. So this program wants to find the first n primes, in this case 3. I want to find the first 3 primes and then just print them to the screen, not do anything interesting with them. And I'm going to do that recursively. Find n primes, takes an int, give me the first 3 primes in this case, and return them in a list of ints. My first base case, n is less than 1. I'm just going to return an empty list. This one makes sense. If somebody asks me for the first 0 primes, I'm going to return an empty list. But also if somebody gets smart and says, give me the first -10 primes, I'm just going to return them an empty list. It's kind of my error handling. If somebody gives me a negative number, here, just have an empty list. There's nothing for me to compute. There's nothing I can do for you if you're going to ask for something like that. My actual base case that's going to be used in my recursive calls is if n equals 1, I'm going to return the first prime, which I know is 2. My base case, trivial input-output behavior. Give me the first prime. Oh, that's just 2. I'm going to return 2. That's my base case. My recursive step, I'm going to recursively call the first n minus 1 primes, and I'm going to build my logic on the assumption that that call is true. That call is getting me closer to my base case. So I have my other 2 conditions, a trivial base case and my recursive call is getting closer to my base case. The last step is my logic has to be sound in my recursive step. If my logic's sound, then by the power of recursion, this is just going to work for us. So let's see if my logic is sound. I'm going to get the first n minus 1 primes, and I have the task of finding the nth prime given the n minus 1 primes, the first n minus 1 primes. So how I'm going to do this is find the maximum prime. There's no mention of order here. The order could be arbitrary, so I'm going to call max, which is going to reduce this list using the max method, which is a built-in Scala method to be able to reduce. We could call dot reduce and expand this out, but we have a nice shorthand method call here to do that for us. So I'm going to find the max element of this list, store that as max prime, and then make another call to another recursive method where I'm going to find the next prime starting at max prime plus 1 and also give it the primes that I already know about and say, give me the next prime. Once this returns, I'm going to append that to my list, prepend that to my list of known primes, and I'm going to return that as the list of the first n primes. That's going to be my return value. This recursive method, it's going to take some candidate prime I and these known primes and check this fairly dense line here, does a lot of work in one line. If this candidate prime is not divisible by any of the known primes, then it itself must be prime. So I'm going to check. Try to divide this by every known prime. If it's divisible by any of them, this will return true, and then I'm negating that. So if it's not divisible by any of the known primes, it itself must be prime. Return it. We found our next prime. If it's divisible by any of the known primes, make a recursive call, checking the next number. Increment I by 1, recursively call this, and check that next number. Keep checking the next number until you find one that is prime. So my logic should be sound here to be able to find that next prime. Return that. I have all my ingredients for solid recursion here. I have my ingredients for solid recursion here. I should have 2 successful recursive methods. And of course I do. I tested this and everything. So let's take a look at where we are in the execution right now. We're at a point where we hit our base case. So we called 4 n primes of 3, put that on the stack. That made a recursive call with 2, which made a recursive call of 1, and we've reached our base case list of 2. At this point, we're going to create a new immutable list and put that on the heap. And it just has the value 2, and then throughout the execution of anything, no matter what else happens, that's always just going to be a reference to the list containing just the value 2. That's the only thing that this is ever going to store. So this frame is going to return. It's going to return that reference at 1. Our next step in our recursive call, going 1 up, is going to get that return value of 1. It stores that in this n minus 1 primes. So n is 2 in this case, so that's the first 1 prime, n minus 1 primes, which is accurate so far, so our assumption is good for this call. We're going to find the max prime, which is 2. Store that. Oh, I didn't fix that. Which is 2. And then we're going to make this recursive call, this call to this recursive method find prime, to be able to find the next prime. I'm going to call find prime of 2 plus 1. I'm checking 3. I'm passing the reference to this list, which is just the value 2. And I'm going to check, is 3 divisible by 2? Nope. That's my only prime. I have to, only known prime. So therefore, 3 must be prime. It's not divisible by any of the known primes. 3 itself must be prime. Return it. Return 3 back to this frame. And here we finally get to see some list action. So we have this prepend of this resolved to 3, and we're going to prepend that to our list at that reference 1. So we're going to take our list at reference 1, and we're going to create a brand new list, which is a copy of the original list, but with 3 prepended to it. So we didn't mess with our original list. We didn't change our original list at all, but we did create a brand new list with that value prepended to it. So we respected immutability, list created a brand new list with that value. And then this recursive call is going to return that list at 2, but at 1 still remains on the heap. So if some other part of our program, some other code somewhere else had a reference that list at 1, there's nothing we can do in our code to interfere with their computation. Since that list is immutable, even if we do want to simulate these changes to the list, we're actually just creating new lists with copies of that data, and then working with those new lists without affecting anybody who has a reference to this list. This is critically important, especially in concurrent code. If we have 2 pieces of code running at the same time, and one piece of code is appending or prepending to a list, and another piece of code at the same time is iterating over that list, we're just asking for trouble. But if we have immutable lists, 2 pieces of code can be doing exactly that, but the prepending code is just going to create a new reference to the list, and if somebody had this list and was working with that, no problem. Both pieces of code just keep functioning without error. There's no potential for error here when we have immutable objects. So we return that reference 2, we're back to the top level call, run our logic under the assumption that this was true. Max prime is 3. We're going to add 1 to that. Call this with 4. 4 is divisible by 2, so this resolves to false. We hit our recursive step and check 5. 5 is not divisible by 3 or 2, so we're going to return 5. We're going to return 5 up the recursion. This recursive call gets 5. That recursive call returns back to first n primes. This gets the, oh, that is another typo. This gets the value 5. Prepends 5 to this list at 2. N primes minus 1 has at 2. Prepend 5, which is going to create another new list. And then we're going to return the reference to that new list. Then we're going to return a reference to that new list to the main method. And the main method is happy. It gets a list, this reference to a list that contains the first 3 primes. Everything functioned the way it expected. Then we have 5, 3, and 2 printed to the screen. Did Jesse say anything about online classes? I assume you're watching this online if you're on Twitch. Like, I already do online classes. The labs is the big open question. I'll have to figure out what to do with labs. I'm waiting for some more official announcement, and then over spring break I'll come up with some brilliant plan that's going to handle our labs in some meaningful way. Any questions on this example? All right, see everyone Friday.